Good morning. I'm Dr.V.Gopinath from Kungunadu College of Engineering and Technology. Today we are going to see about a heat engine, heat pump and refrigerator. This topic comes under engineering thermodynamics. First we'll see about that heat engine. The heat engine means we have to calculate the efficiency. The heat engine is a device and produce work by supplying the heat from the hot reservoir. So your engine will have the hot reservoir and cold reservoir. The hot reservoir is T1 and cold reservoir is T2. So the heat supplied from the hot reservoir is Q1 and heat rejected to the cold reservoir is Q2. So the heat transfer from higher temperature to lower temperature. So the one form of the energy is converted into the another form. So the heat energy is converted into the work energy. So the heat transfer from higher temperature to lower temperature and we are extracting the work from the engine. So this is the principle of heat engine. So we are calculating the efficiency of the heat engine. Efficiency equal to net work output divided by total heat input. So net work output is W divided by the heat supply is Q1. Your work done will be heat supply minus heat rejection. So that the efficiency will be W by Q1. So that Q1 minus Q2 divided by Q1. So here that heat will be that according to the entropy Q equal to TdS. So that the first one Q1 we can write it as T1 ds, next to Q2 is T2 ds divided by T1 ds. So the common term is change in entropy ds, so we can remove it, so that the formula will be T1 minus T2 divided by T1. So from this we can find out the efficiency equal to 1 minus heat rejection by heat supply, which is equal to 1 minus T2 by T1. So this is your heat engine principle. Heat engine means we are going to calculate the efficiency, the heat transfer from higher temperature to lower temperature. From that heat energy we are extracting the work output. The next thing is heat pump. The heat pump and refrigerator are same principle, but only thing is where the heat is extracted and where the heat is supplied. So first we will see about the heat engine, sorry, heat pump. Heat pump is a device used to supply the heat to a hot system. So the heat pump is, it is pumping the heat from your atmosphere to your room. So you can take it as higher temperature T3 is our room and your lower temperature is atmosphere. So the heat is pumping to your room from the atmosphere with the help of your supplying the external work. So you can see that the T4 will be the atmosphere, your T3 is your room, and your heat pump you are supplying the work, so that the COP will be, the coefficient of performance will be heat supplied divided by work input. So heat supplied is, the heat supply is Q3 divided by your work input is W, which also you can write it as heat supply minus heat rejection. So that Q3 minus Q4. So in terms of temperature, T3 divided by T3 minus TL. Next one is you will have the refrigerator. The refrigerator is a device used to remove the heat from the cold system. So refrigerator is removing the heat from the cold system. Your heat pump is supplying the heat to your hot system. You can see here your T3 will be your atmosphere. The diagram, you can look at the diagram, both are similarly same diagram. Only the change is the atmosphere position is changed from your heat pump to refrigerator. In your heat pump your T4 is your atmosphere and your refrigerator your T3 is atmosphere. So here your lower temperature will be your room. So from your lower temperature you are extracting the quantity of the heat and which is supplied to your atmosphere. Okay, so that the COP equal to heat extracted divided by work input. Heat extracted means your lower temperature, so that Q4 divided by Q3 minus Q4. In terms of temperature, T4 divided by T3 minus T4. You look at the heat pump and refrigerator. Heat pump, it's pumping the heat to the room. Your refrigerator is extracting the heat from the room. Okay, so this is the main difference of your heat pump and refrigerator. So heat pump and refrigerator, your output will be in terms of coefficient of performance. Your heat engine will be in terms of efficiency. So you have to see these formulas only. Okay, we are going to apply these formulas for your applications. We will see the problem based on your heat engine, heat pump and refrigerator. The problem is a reversible heat engine operating between the reservoir at 900 Kelvin and 300 Kelvin. They mentioned that heat engine operating between 900 Kelvin to 300. So you can draw the diagram of heat engine. The higher temperature will be 900 Kelvin and your lower temperature will be 300 Kelvin. Drive a reversible refrigerator operating between the reservoir at 300 Kelvin and 250, and that heat engine drives the refrigerator which is operating between 300 Kelvin and 250. You draw the refrigerator diagram. The lower temperature will be 250, your higher temperature will be 300. You can draw. So your higher temperature side will be your QS, your lower temperature side will be QR. So from your left hand side, your heat engine heat supply is QS1, your heat rejection will be QR1. Your right hand side refrigerator, your heat supply side is QS2, that is 300, and your heat rejection will be QR2 will be 250 degrees centigrade. So they are given the 4 temperatures of your system. The heat engine receives 1800 kilojoule heat from the 900 Kelvin. So the 900 Kelvin is your higher temperature. So from that you are receiving the heat. So that QS1 equal to 1800 kilojoule. So you will have the QS value which is 1800 kilojoule. The net output from the combined engine refrigerator is 360 kilojoule. The net output combined from the engine and refrigerator. One thing, that heat engine we are extracting the work, your refrigerator we are giving the work. So extracted work from your engine, some quantity of work we are supplied to the refrigerator. So that extracted work will be W1 from the heat engine. The supplied work to your refrigerator is W2. So when you are taking for net output means W1 minus W2 equal to 360 kilojoule. Find the heat transfer to the refrigerator. Heat transfer to the refrigerator means you have to calculate the QR2 and the net heat rejected to the reservoir at 300 Kelvin. The net heat rejected to the 300 Kelvin is, one is from the engine is QR1, another one is from your refrigerator is QS2. So we have to calculate the QR1 plus QS2. Okay. And we can split it into two. One is your heat engine, another one is your refrigerator. Your heat engine, you know the temperature, higher temperature, lower temperatures. So higher temperature is 900, your lower temperature will be 300. So the heat engine efficiency formula is higher temperature minus lower temperature divided by higher temperature. So 900 minus 300 divided by 900. From that you can calculate the efficiency will be 66.6%. And one more formula in terms of work and heat supply. Your efficiency will be work done by heat supply. So that work done is W1, heat supply is QS1. So QS1 value is given in the problem is 1800 and efficiency we have calculated. So from that you can find out what is the W1, that is the work output from the heat engine. W1 is 1200 kilojoule. And we know that work done equal to heat supply minus heat rejection. So that QS1 minus QR1. So we know QS1 and W1. From that we can calculate the QR1 which is equal to 600 kilojoule. Next we will move on to the refrigerator. The refrigerator we know the two temperatures. Your lower temperature will be 250, your higher temperature will be 300. So that you can substitute that 250 divided by 300 minus 250. The COP you can calculate it is 5. COP of the refrigerator is QR2 divided by W2. We know the W1 is 1200. The W1 minus W2 will be 360 which is given in the problem, that is the net work output. So from that you can calculate the W2, the value will be 840. So W2 value we know, COP value we know, from that you can calculate the QR2. So the QR2 is 4200 kilojoule. Then you know the W2 equal to QS2 minus QR2. So 840 equal to QS2 minus 4200. From that you can calculate the QS2 which is 5040 kilojoule. So first one is heat rejected from the refrigerator is QR2 is 4200 kilojoule. The next one is net heat transferred to the reservoir at 300 Kelvin. The 300 Kelvin from your heat engine is QR1. The next one is the 300 Kelvin from your refrigerator is QS2. So 600 plus 5040, you will get the 5640 kilojoule. So this is the problem on your heat engine and your refrigerator. Similarly, you will have that combination of heat engine, heat pump and refrigerator. These are the formulas, this is that system principle, and you apply it, you will get the answer.